Week 14, part 6. Let's do some examples having to do with the resolution limits of optical systems. We'll start with the human eye and ask the question, what's the theoretical limit of human vision? How good could it be, assuming it was perfect in all other respects? What would be the limit placed on it by this diffraction effect? So first you have to realize what is causing the limit. Remember, it's a matter of the aperture, the diameter of the aperture. That's not the eyeball. That would just be the opening in front of the lens. It's the pupil. The pupil is what defines the aperture size in your eye. And pupils can be various different sizes, perhaps as large as 9 millimeters for a young person who's got fully dilated eyes. More typically, we have pupils that are something like 5 millimeters or 6 or 7 sometimes. But I'm going to use 5. And what wavelength we're using? Well, of course, human vision covers a range, but it is dominated by the green area. That's where we're most sensitive. So that's what I'll use, is 550 is kind of in the middle, and that's a greenish color. So how fine a detail can we see? What is the angular resolution? How close can two things be in angle out here? And we can still distinguish them as two different objects that way. So if we calculate that for human vision, we use this formula, 1.22 lambda over d. This is the Raleigh criterion. So put in the numbers, 1.22, and then lambda is going to be this 550, but that's nanometers, so we have to take that times 10 to the minus 9 to put it in meters, and then divide by the diameter, the aperture diameter. In this case, that's 5 millimeters. I'll put that again in meters, 5 times 10 to the minus 3 meters. And if you do that calculation, you should come out with a very small number. It has 3 zeros and then a 1 and a 3. You might wonder about the units. The 1.22 is just a number. So we've got meters divided by meters. Looks like we have no units. Remember, we're calculating an angle, and radians is the unit that has no units, sort of. So that's coming out in radians. That's what naturally comes from this formula. You can convert that very quickly to degrees. That's the same thing as 0.0077 degrees. Commonly, when things are that small, if we're working in degrees, we do go to degrees, minutes, and seconds. And so this can be converted further by multiplying it by 60 seconds, or 60 minutes in a degree. And that gives you the answer of 0.46 minutes, or about a half of a minute, half of an arc minute, sometimes they're called. So about half an arc minute, that is the theoretical limit. So about 1/2 arc minute. And that is an easy number to quickly calculate. You might wonder, how does that compare with actual vision? Well, if you go by the Snellen eye chart, surely you all have been subjected to this. This is the thing with the great big E on it, and then A and B, Q, and a bunch of letters on down the line. And each line corresponds to different levels of vision. And somewhere down here is the 20/20 line. And that 20/20 line is supposed to be perfect vision. At least people call it that. That's a terrible way to call it. It really should be just called good enough vision or something like that. That line corresponds to a resolution of about 1 arc minute. And so you'd think, oh, well, we must not really have that good a vision. We could be a factor of 2 better than that. But actually, this thing is pessimistic. Most of you probably, when you took the test, were able to read the next line below it, 2015, meaning that you have vision that's somewhat better than that, maybe 0.75 arc minutes or even better. And that's quite common. It's a funny line that's put on here that's called 20/20, and I think it comes about as much as anything just because 1 arc minute is a simple round number. And so that was decided on as kind of a standard to say, well, that's vision that's reasonably good or something like that. But in fact, most of us have vision that's better than that. And in fact, when I've had my students try various means to test our resolution, and I don't really know don't have the equipment to do this the proper way, let's say it that way. But my students have gotten numbers very close to this, in some cases better. Now this, using the Raleigh criterion, is in fact, as I've said, it's a little bit pessimistic, and various experimental approaches to see, well, what can people see with telescopes and such, have turned out that, well, in fact, you can probably see all the way down to 1 times lambda over d, which would give a different number that would be somewhat smaller. So that gives a bit of an idea of the resolution, but that's in angular terms. Can we make this something a little bit more concrete? What can you see with that? Well, it depends on how far away the thing is. Let's just say you're trying to look at some tiny little thing. Most of you probably have let's say you have a near point of 10 centimeters. That means that's as close as you can hold something without using some special magnifying lens, and that would be cheating. So if that's your near point, 10 centimeters, then how small can you distinguish objects without using a magnifying lens? Well, so think about what we've got here. Here's your eyeball again, and you're going to hold something from the eyeball some distance away. Well, exactly 10 centimeters away. That's as close as you can get before it starts being out of focus. And now the question is, how close can these points be? And you can still distinguish. If we take this number up here as your resolution, actually, let's go up and use the radians. That's much easier. And that's the closest in angle that these can be. Then how close can they be in distance when they're 10 centimeters away? So let's call this maybe a delta y that we're trying to calculate, a difference in y position. And out here is a distance, I don't know, I'll call this s, is 10 centimeters. Then this angle, we'll still call this angle theta. Theta, if you think about it, for small angles at least, is again just the distance around the arc divided by the radius. That's how we defined an angle in radians. So we could write this as just delta y divided by s. It's that simple. And we're trying to get delta y knowing theta has to be that number and knowing s is the distance. So let's just rearrange this a little bit. Solving for delta y is going to be theta times s, or it's going to be 0.00013 radians. I won't even bother to write the radians, times 10 centimeters, or 0.1 meters. And what do we get when we do that? Well, you get 1.3 times 10 to the minus, it's the minus 5. Why did I write 3? 10 to the minus 5 meters, or another way of writing this would be 13 micrometers. That's how small a detail that you can see if you had perfect vision. Now, in fact, we don't. We probably don't have vision that's that good, although some of us would come maybe quite close to that. As I say, when my students have measured things, they get numbers that are in that range. So you might be able to see, if you have a near point of 10 centimeters, two objects 13 micrometers apart, and distinguish them as two objects. Somebody like me with a near point of 25 centimeters, you can go through the same calculation, and I find that it's more like 34 micrometers is what it leads to. And that's simply because I can't hold the object as close. My eyes won't focus that close unless I use some kind of special lenses. So at a near point of 25 centimeters, you can't see as fine a detail. You wonder how fine is that? You could compare that. About the most common thing that people know about is the human hair. Unfortunately, it's not a very good standard because the human hair ranges quite widely. What I've read is 17 micrometers up to 180 micrometers. So if you have extremely fine hair, um, uh, blonde hair tends to be more fine, and on the other hand, black hair tends to be thicker and heavier. Even the individual hairs are thick. Um, so most hair is somewhere in the middle. One number has been proposed as 75 microns. So at 75 microns, I can just barely make out that the hair has any width to it at all. It looks like just a line to me, and I wouldn't be able to tell the difference between, um, well, I wouldn't be able to tell that that was other than an infinitely thin object. You folks holding it closer can more likely see and discriminate even from between different types of hair and see which ones are wider and which ones are narrower with that kind of resolution. Okay, so that's about human vision. Um, here's another example, just very quickly. How far apart could car headlights be, and where you can still distinguish them as two headlights as opposed to just one light? When does that separation happen? In my experience, when I'm driving at night, it seems like anytime a car comes over the hill, I can always see two lights. I don't ever just see one. So does that make sense? Let's imagine that typical car headlights are, so here's our car with its headlights. And we imagine that the separation between these is 1.5 meters. I just did a little checking on how wide cars are, and they're usually a little wider than that. So that's maybe a reasonable guess as to the distance between the two headlights. Now, how far do those have to be away to form an angle at our eye that goes with this 0.00013? And we're still assuming perfect vision here, but as I say, we're close to that. So how far away? Now we're trying to get the distance in this case. So it's still the same formula. The theta here would be delta y, we should call it x in this case, I don't know, over s. And now we're trying to get the distance. S is going to be delta y over theta. And so that would be this 1.5 meters divided by theta, which is this 0.00013. And there are no units on that one. It's radians. We can just leave out the units. We'll put this in meters and we'll get a distance in meters. And if you do this calculation, you get 11,177 meters, or about 11 kilometers. Wow, okay. This is about 7 miles. So that explains why when you're driving ordinarily, you don't ever see those headlights merge together unless you don't have very good vision. But you should basically always be able to see them separate unless you are seeing in truly far away on the highway. So once in a while you can see a highway that far away, but not very often. Okay, that was human vision. Now let's have some fun with a little more esoteric one. And that is the question of what can spy satellites see? So here is the Earth, and up in orbit above the Earth, not nearly that high probably, but here's a spy satellite, and it is looking with some kind of camera down at the Earth and taking pictures. And the question is, what sort of resolution is possible using a spy satellite like this? Now you might think, well, surely they can get as close as they want, but they're limited. They have to be out in space, and so that puts kind of a limit on how low they can be. And the limit, it's around 100 kilometers below which satellites can't stay up at all. So let's put it up just a little higher than that, and say it's orbiting at an altitude of 150 kilometers. So if it's up at 150 kilometers, that's a very reasonable number. They don't go much lower than that, and you'll see in a little bit it doesn't matter a whole lot. And I want to turn this question around. I don't want to see, we'll at the end, we'll turn it around and see, well, what can they see? But right now, I'd like to ask a question, which is, can they read a license plate? So say we had, an Indiana license plate like this, and the question was, can they read these numbers from up there? Well, it gets to the question of, well, how fuzzy does this have to be before you can't read it anymore? And that is actually an interesting question to try to answer. Essentially, you have to say, well, how much can I fuzz this out and still be able to tell that I've got two black lines here separated by a white line? That's the kind of question that you're asking. And if you lay this on here, these are centimeters, and I think you would agree that if we fuzz this out by a centimeter, it's going to start to get very hard to read. And much beyond a centimeter, and you would not be able to read it anymore. If your fuzzing is that large, you're just not going to be able to tell much difference anymore. So kind of relating this to the Raleigh criterion, we're going to say, well, maybe a fuzzing, an airy disk that's about a centimeter in size would be sort of the limit if we're going to try to read a license plate. Now, there's a little detail here we're not even going to bother with, and that is that the spy satellite is looking straight down, and you can't read a license plate if you're looking straight down from above, but we'll forget about that. They would have to shoot at some kind of an angle. But I just want to see if we can answer this question. So let's ask how big an aperture would be needed in order to do that. How big would the mirror or lens on that spy satellite have to be if we want it to be able to capture, if we need a resolution of 1 centimeter in order to be able to see the details that we're trying to see? So if you're in charge of designing one of these satellites and somebody comes to you and says, okay, we want to have a resolution of 1 centimeter because of what we want to be able to see, what would you then need to design? How large a mirror or lens would be necessary? Well, let's figure out what angle this corresponds to. So now, drawing this in a little different picture, here's our camera, if you like, on the spy satellite. And it is going to be looking at something that's far, far away and trying to discriminate these details that are 1 centimeter apart. And we're trying to figure out, well, what angle does that require if it is, in fact, 150 kilometers away? So what angle is associated with two objects that are a centimeter apart and they're 150 kilometers away? It's the same thing. We're defining the angle by just this distance divided by the distance away that they are. The separation, so this would be this 1 centimeter divided by 150 kilometers, but we got to fix the units here real quickly. So 1 centimeter I would rewrite as 0.01 meters. 150 kilometers, well, I could write that as 150 times 10 to the third meters. And if you do all that, you're going to come up with a number of 6.7 times 10 to the minus 8. This is the angle. What have I got units for this? This is meters divided by meters. That's nothing. Oh yeah, nothing means it came out in radians. Okay, so that's the needed angular resolution to get this distance resolution of 1 centimeter. Okay, then how big is the needed lens or mirror on this satellite? Well, that goes back to the Rayleigh criterion. So remember, theta is 1.22 lambda divided by d. So rewriting this, because we're trying to get d this time, that's 1.22 lambda divided by theta. So 1.22, and now I'll put in lambda. Well, what are we going to use? Well, you have to ask what wavelength of light are we planning to use on our satellite? And maybe it comes back, we're going to do visible light. Okay, then let's do it with 550 times 10 to the minus 9. You could pick a different number, but this is the middle of the visible spectrum, so that's what I'll use. 550 nanometers, 10 to the minus 9 meters. And then we divide by our angle up here of 6.7 times 10 to the minus 8 radians. You could put in here, but remember you can just eliminate radians whenever you want. And we're going to get a D coming out of this that is in meters per radian, but you get rid of the radians. So the D, when you calculate that, is very close to 10 meters. 10 meters. We need a lens or a mirror that's 10 meters in diameter. Now, there are such mirrors on Earth. There are a few telescopes that have a diameter of 10 meters. That's about as big as anything is right now. Those are the very biggest telescopes on Earth are 10 meters. There's nothing up in space that size. Even the James Webb that's going up in a year or two. What is its diameter? I think it's 5. No, it's more than that. It might be 8. It might be getting close to this. I don't remember exactly. But there's nothing up there right now that's this diameter. At least I don't think so. I would not be the one to know. But what is up there is Hubble. And Hubble has a primary mirror that is 2.4 meters in diameter. And you might ask the question, well, if Hubble has a 2.4 meter diameter main mirror, how big a mirror do they have on a spy satellite? And a reasonable guess would be to say probably about 2.4 meters. It wouldn't be surprising to know that the spy agencies, which seem to have huge budgets, have been able to launch something of a similar size. So if they've got a mirror this diameter, what can they do? What resolution? What resolution do they have? We seem to have calculated that it's unlikely that they can actually see 1 centimeter. What can they do? So we're kind of turning the question around. With a 2.4 meter diameter, what resolution? Hubble isn't designed to turn around and look at the Earth. I don't know if it could or not, but they don't anyhow. But what would be possible with the spy satellite? So let's just calculate that. Now what I'm going to do is be a little bit more realistic. And so we would normally say this is 1.22 lambda over d, but I'm going to say, no, these folks have pushed everything right to the limit, and they aren't using the 1.22. They have gotten it down to 1.0. The Rayleigh criterion is 1.22, and you can do better than that. And I'm going to assume that they have done better than that. And another thing you can do is change the wavelength. There's no reason you have to work right in the middle of the visible. Let's push it, and you can see, well, which way would you push it? If you want to get smaller resolution, you use shorter wavelength light. So let's go down to the blue end of the spectrum and put in 400 times 10 to the minus 9. That's right at the edge of visible spectrum. And then down here we put 2.4 meters. And what we get out of this in angular resolution is 1.67 times 10 to the minus 7 radians. And now if we look down, okay, what kind of resolution does that give you in terms of centimeters or inches or whatever down on the Earth? How small can things be that they can still see? So that's back to this other idea that theta is delta y over s, and we're interested in delta y. So delta y is going to be s times theta. So what distance away is it? Well, it's 150 kilometers, 10 to the third meters. And then I put this angle right in here, 1.67, 10 to the minus 7 radians. And out will come a delta y, which is 0.025 meters, or if you like, 2.5 centimeters, which is about 1 inch. So likely from a spy satellite, the powers that be are able to see things that are only an inch apart and see them as two things. That probably doesn't give you a very good picture of a person's face, if that's what you're after, but you certainly can see the person and you can see an awful lot about them. You can very easily count people. At that resolution, you could even fairly easily, I think, at least identify people that have sort of obvious characteristics. I think you can tell the difference between men and women, that sort of thing. So that's probably what's possible. Of course, this is a spy satellite. It only works if the sky is clear, and it also only works outside. So if you're inside a building, this isn't available. Anyhow, there you go. Those are a couple of examples, and there's some other interesting ones that you'll be working on in the website.